In this video, we're going to take a look at rotational dynamics, in particular, conservation of energy, where we factor in rotational kinetic energy. So let's take a look at three different objects and consider the rotational inertia of each. So here's a thin hoop where the rotational inertia is just going to be mr squared. And then a basketball, or maybe a bowling ball would be better, because a basketball is fundamentally hollow, but I'm just going to go with basket, bowling ball, a bowling basketball. How about that? Where I is equal to, so representing a sphere, of course, 2/5 mr squared. And then a disk where the rotational inertia would be 1/2 mr squared. Right, so this coefficient that comes up front is also called the radius of gyration. And it has to do with how we add up the incremental sections of mass and how far they are from the axis of rotation. So the hoop is really easy because all the mass is on the outside. But the bowling ball, you can see at the sort of north and south poles, the mass is a little bit closer in. So that makes the rotational inertia a little bit less and makes the ball a little bit easier to spin. And then the disk. And so given these two, this actually has slightly less rotational inertia because it's 0.4 times mr squared instead of 0.5. So let's give all of them a velocity. Let's suppose they're cruising along and doing about 2 meters per second. And then we want to then see how far they go up this ramp. And instead of having a given height, we'll just say question mark. Why don't you figure that out? Now, the example I'll do is for the disk. But then we can do a conceptual comparison for these and how do we think the other ones are going to perform? Which one's going to wind up going highest up the incline? So our kinetic energy is a maximum as it's rolling along. And again, assuming no friction, and the potential energy is equal to 0. And then when we get up here at the highest point, then the potential energy is going to be equal to a max, and our kinetic energy would be equal to 0. So we can equate these two, right? So the kinetic energy in rolling is going to be equal to the potential energy at its highest point. So that's going to be mgh. Now, if you're curious about the distance it's going to roll up the incline, then that's going to equate to height when we incorporate the angle. So h is going to be equal to d sine theta. If that's an issue for you, but in our case, it's not. So we're just looking for how high it goes. All right, yeah, so now let's do kinetic energy, and that's going to have two parts to it. So we're going to have both traditional translational kinetic energy, 1/2 mv squared, and then rotational kinetic energy, which is going to be 1/2 I omega squared, which is kind of a strange looking beast, but that's okay. Now, it says the velocity is 2, but then I have angular velocity here. And you notice that I didn't apply, I didn't give any m's or any r's here. And it turns out that none of those actually matter. Which is kind of an interesting result. So 1/2 mv squared. And now what we'll do is we'll do some substitutions. So for I, let's do the disk. And so what we can do is take this 1/2 mr squared and we can drop it right into here for the rotational inertia. So that's going to be 1/2, and now I put in the rotational inertia, which is 1/2 mr squared. And now here's probably the most important thing we're going to do in this example is that the linear velocity and the angular velocity are not two different things. If it's indeed rolling and not slipping, then that means that for any given velocity, linear velocity, there's going to be exactly one and only one angular velocity. So, and they equate to each other based on the radius. So omega is going to be equal to V over R. And capital R, lowercase r really doesn't make any difference. So then when we're going to square that also. So this is going to be V over R squared equals MGH. So we pull back from this for a minute and just take a look. So we've got M's in every, again, capital, lowercase, doesn't matter, not case sensitive. And so the M's are going to be able to cancel out. And we also notice that the R squareds are going to be canceling out too. So let's go ahead and do that. So M's are gone and the R squareds are gone. So now when we go to do this, we're going to have 1/2 V squared, which is the contribution that comes from the linear kinetic energy. And then we have 1/2 times 1/2, so that's 1/4 V squared is equal to G times H. Yeah, so before we actually put some numbers in, let's think about where this came from. So this 1/4 is from our disk. If we were doing the bowling basketball, then we'd have a 2/5 in here. So then this number would be 1/5 instead of 1/4. What does that mean? Well, if it's 1/5, then this number is going to be slightly less, which means that the height is slightly less. Remember that we said that the velocity is the same for all of them. And since the velocity is the same for all of them, that there is energy stored in not only linear motion, but also rotational motion. And so the one that's got the biggest rotational inertia is actually going to go highest up the ramp. If we did a hoop and we put in just mr squared here, we'll have 1/2 plus 1/2. So that would give us the biggest H. So let's finish this off and take a look at some numbers. So 1/2 plus 1/4 is 3/4. V squared equals G times H. And then we're going to solve for this and see what we get. So 3/4 of 2 squared equals 9.8 H. And now we'll just solve really quick. And so 2 squared is 4, of course, so that's 3. So the answer is just 3 divided by 9.8. And I get 0.306 meters. If this was the hoop and this is 1/2, then it's just going to be V squared divided by 9.8. So that'll be 4 divided by 9.8. And so that's going to be approximately 1/2 meter. So the hoop would go up higher because it's got more kinetic energy stored in rolling than the disk does. Whoops, here we go. It's a little bit better. All right, I hope that helps.